and for a smooth function f, this topology induces some topologies on the stabilizer and the orbit. We denote by DIDM a connected component of the identity map in DM, and by OFF the connected component of the orbit containing F. And we also set S prime F to be the following intersection. By a Morse function f on M, we will mean a smooth function which satisfies the following two conditions. All critical points of f are non-degenerate and belong to the interior of M, and the function f takes constant values on each boundary component of M. And Morse function f is called simple if every critical connected component of every critical vector set contains a unique critical point. And f is called generic if each critical vector set of f contains no more than one critical point. Let f be a Morse function on smooth orientable surface M, and let delta be a partition of M into connected components of local sets of M. It's well known that the quotient space M by delta, which we denote by gamma f, has a structure of an one-dimensional CW complex and is called a Kronrod-Reeb graph of F. Let P be a projection map induced by F. Okay, denote by out gamma F the group of homeomorphism of the graph of function F. Each diffeomorphism H from S prime F preserves local sets of F. And so F induces the homeomorphisms of gamma F such that the following diagram commutes, and the correspondence H to rho H is a homeomorphism. And the image of S prime F under rho is a finite group in output gamma F. And we will denote it by GF. So the group GF is a group of automorphisms of Kronrod-Reeb graph of a function F induced by isotoking to the identity map and F preserved in diffeomorphism. Namely diffeomorphisms from this group. Homotopy properties of stabilizers and orbits of Morse functions on smooth compact surfaces were studied by Elena Kudryavtseva, Sergei Kronrod-Reeb, and his students. Groups GF play the essential role in the description of homotopy types of the orbits. Sergei Kronrod-Reeb and Anna Kravchenko studied these classes of such groups and their subsets. Let GM be the integral set of isomorphism classes of groups GF for all Morse functions f on M. By G, SMP, and Ggen, we will denote the subclasses of Gm, which correspond to classes of isomorphisms of group GF for all simple and all generic Morse function on M. Anna Kravchenko and Sergei Maximenko gave a full algebraic description of classes Gm and GSMP for all compact orientable surfaces which are different from two sphere and two torus, and prove that the class Gen is trivial. Our aim was to extend this result by giving a full description of the classes G and GSMP for Morse function on two torus. To state our main result, we need a notion of rest products of groups with cyclic groups. So let G be a group and N be integers. And we consider two actions, alpha and beta of Zn and the product of Zn and Zm on powers of G. Given by formulas. And with respect to these actions, semi-direct products will be called rest products of G with the N and G with the product of Zn and Zm. A more general definition can be found in the book of Calderon. For a natural N, let Pn be a minimal set of isomorphism classes of groups which satisfies the following two conditions. The first one, the unit group belongs to Pn, and the second one, if A and B belong to Pn, then the direct product A and B and rest product A with Vn belong to Pn. And let also P be a linear set of isomorphism classes of groups which contain Pn as subsets for all n. And we have the following theorem. So for each compact oriented surface M, which is not two sphere and two torus, the following classes coincide. And for all compact oriented surface, the class G for generic Morse functions is trivial. An algebraic structure of these groups from Morse functions on S2 is more complicated than for the case of Morse functions on compact surfaces on G equals greater than 1. And recently, Sergei Maximenko and Anna Kravchenko described special subgroups of this group for such functions. It is well known that the Kronrod-Reeb graph of a Morse function on two torus is either a tree or contains a unique cycle. The class of groups GF from Morse functions F on T2, whose graphs are trees, will denote by G0, and in case of cycles, G1. And to describe classes G T2 and G SMP2, We need three classes, E0, E1, and E2. We see this in this slide. And the following theorem is our main result. The following classes coincide. A reference can be found in these papers. And that's all. Thank you very much.